Good evening all. Before getting started with the week, let me introduce myself again to those of you who are watching this video on YouTube. So myself Durga Prasad. So I'll be the TA for this online sessions. So the aim of these sessions is to help you solve your assignment problems. At the same time, we'll also kind of discuss any of the doubts that you have during the week lectures or any of the previous weeks. We'll get started with this week's session in a couple of minutes. Yeah, I'll get started with a quick summary of the lecture videos of this week, and then we'll get started with the problems. So maybe this will take around half an hour or so. So if you have any questions, we can discuss them first, and then we can go through the summary, or we can do it any other way you want. Do you have anything that you want to discuss before me getting started? Or I think it would be better if I summarize first, and then if you have any queries, so that can fill in later. If you have any doubt in the meeting, you can stop me in between. So this week, okay, yeah. So this week there are a couple of concepts. One is on how do you transform your optimization problems. Essentially, you have say problem one, like you have two different problems. In order to solve problem one, what you do is solve problem two. Instead of solving problem one, you solve problem two, and then somehow do a transformation to get the solution of problem one. So in a sense, these two are equivalent as long as you know how to move from second problem to the first problem. So there are different kinds of transformations that I discussed in this week. One is the scalar multiplication, one-to-one mapping of the domain, monotone slack variables, linear equality concept, different. We will discuss each one of them one by one. And the second concept is on convex analysis. There are different definitions. These are more, this week's lectures mostly focus on what these definitions are and how this can be used is something that will be come up in the upcoming lectures. So for now, I'll just restrict myself to what these definitions are, and we'll take a couple of examples to see how, to take an example and see whether it follows the set of rules that we have defined for whether it is an affine set or not, whether it's a convex set or not, and different examples for that. So coming to the first one, so this is a standard optimization problem. We want to minimize some objective function, minimize f of x, and x is my x belongs to certain s, and this s is something that is specified in this way. So it is specified by a set of inequality constraints and also a set of equality constraints. So what this s is can in some particular space, let's say in 2D in R2, this could be something like this. We discussed this last week as well. So when you, if you want to, if this is my feasible domain, this entire thing in the circle is my feasible domain, then in order to represent that, all I have to do is just specify something as the center is and radius is say r. If I put equal to r square, then it only represents the boundary of it. So whenever we say equality constraint, it only represents the boundary of that particular one. And if you put an inequality instead of equality, then it includes both the boundary as well as the interior points. So when you club both of these, both inequality and the equality constraint, essentially we are kind of describing my set domain, yes, in this particular fashion. So now what are the different kinds of transformations that we can do on this? The first one that comes up is the scalar multiplication. So we multiply the objective function with some scalar alpha, and we multiply all the inequality and equality constraints with some other scalars beta and gamma. Provided if alpha is positive, beta is positive, and gamma not equal to 0. In those particular cases, what would happen is the variable that I'm searching here is x. So if you consider in this, in the previous circle, so when I'm searching, what I'm doing is I'm trying different combinations of x comma y. I can try some point here, I can try some point here. There is an objective function different from this is just a domain. The objective function will be in 3D. So if you put another axis, z axis, something like this, then the objective function could be something depending on what the function is. In the z direction, it can be something like a cone, or it can be sphere, or something else. We don't know what it is as of now. But when we are searching only in this domain. The x and y possible combinations will only lie in this value, and the third axis is my objective function. So with that notation, in this particular way, when I am scaling my objective function and scaling the constraints, what we are doing is essentially changing this value. So even if you see the equation here, if you multiply this entire equation with some particular constant alpha, yeah, you have something? Yes. Yeah, sure. That was okay. That comes up. We did that in the implicit function theorem. Like we converted a 2D problem to a 1D problem. But this is not that. This is different. Yeah. Yes. Yes. Yeah. So, for example, you might have a problem where, let's say, your objective is to, let us take an example. So, you want to move some particular point A to point B, and you want to find some shortest route or something. But then there are certain number of routes. This is one route, and this is one route. Let's say these are only two routes available. So, how do you specify this in your optimization problem? I can always say that as long as you follow one particular route, the total distance or whatever total time, whatever is that, should be minimized. But how do you specify that thing? Then I will fix some origin here. Let's say I fix my origin at A. This is my 0, 0. Then this curve I will represent using some equation, right? In 2D, this will be like, say, y equal to, say, this is sine x or something. So here I get an equation in terms of x and y. All I wanted to do is find some path. So my objective function will be in terms of x and y subjected to this constraint. I cannot move, I cannot go in this direction. I cannot go in some other direction. I can only move along this particular path. So in order to represent that, I have to put an equality constraint. This is one kind of constraint. Now comes the inequality constraint. You can move in any direction as long as you stay within, like if you have a football court or something. In the football court, the players can move anywhere, but they should be confined to this region only. They cannot go outside this, like outside the stadium and play. So then you need to specify not just the boundary, like you know the boundary equation. Boundary will be some y equal to f of x, say ellipse equation or something, or some rectangular equation, say you have a rectangular field. You know the coordinates of the rectangle, and that will specify, like with equality constraints, you can say x equal to something, sorry, y equal to something, x equal to something, y equal to something, and x equal to something. That will only specify the boundaries, but the players can move interior as well. So which means you need to say that as the condition will be something like x is between, say, this is a and b, a less than or equal to x and less than or equal to b, something like this. And similarly, you have some coordinates c and d here, then d less than or equal to y less than or equal to c. So you have inequality constraints. So whenever you have certain region to be covered, then you have to put inequality constraints. So in general, what we can say is these inequality constraints, it cannot always be in straight lines. It can be some curves also. So you have ellipse sign, something like this. Then you can specify something like this, like a circle kind of thing. You can have a circular field, and you'll put something like minus r less than or equal to r square. In general, you can say like g of I less than or equal to 0. That is a general kind of constraint that will compress one entire region. And x here is not one variable, x belongs to Rn. So essentially x is equals to some x1, x2, and so on. Xn. Uh, the one that you were referring to, converting 2D to 1D problem, was something we discussed last week. The problem there was we had a like we defined our first order optimality condition. Maybe I'll just open up the last week one so that. Yeah. So the problem here was we had a problem with two variables. So this is in R2, but there is also a constraint in R2, both the constraint and that's in R2. But in order to find the optimal solution, we need our domain to be an open set, which is not always the case. In this particular case, domain is not an open set in the way that, our premier first condition is del f equal to 0. But in order to do this, we need to have an open set, which we do not have. So in order to make it an open set, we converted y in terms of x, then it becomes an open set, and then I can solve the problem using the first order optimality condition that is already established. That was what we were trying to do last week. This is different from that. Now what? Yeah. Now what we are trying to do is just understand, I have different problems. How are each of these problems related to each other? The main conclusion would be like, if you see in the first case, if you do in the let's say scalar multiplication, when you multiply this g of x with some pi, so what we are doing essentially is multiplying both of these things. Just by scaling, what we are doing is maybe the circle's radius will increase, so accordingly everything will be scaled. But then my search space is still the same. I'm still searching the same values of x and y. So my domain or the amount of points that I have to search will not change by this. Similarly, when you have h of x equal to 0 with gamma j not equal to 0, the values of x that I have to search for, or to put it in other words, the number of combinations I have to search for to determine the optimal value are not going to change just by this transformation. So what we are trying to understand is, how are these two problems related? How is this problem related with the original problem? If I do not have alpha, do not have beta, and do not have gamma, in both the cases, my optimal x will remain the same. Like if I can get optimal x in this problem, I can get optimal x in any scaled problem. Or in other words, it can be like you have infinite number of ways to pose the same optimization problem. You can pose this optimization problem, or without alpha, beta, gamma, you can also pose a different optimization problem and end up with having the same answer. Your objective value will be different, but then the optimal value of x corresponding to that will remain the same. So that, yeah, here we just say gamma not equal to 0. So this eventually would mean h of x equal to 0. So we'll get back the original constraint. So in this particular case, if you take a line equation or something and then multiply the entire line equation with something, nothing will change. The line remains still the same. So your feasible region shape will not change. So your feasible region will always remain the same by this scaling. So if you draw it on a graph paper and see, then nothing will change. Everything will look the same. That's what we are trying to say in this. So scaling doesn't change anything. The only thing that will change is your x star will remain same, but then f of x star will change. Now, if you multiply with that with alpha, then your objective value will be scaled by alpha. That's the only change you will get with scaling. But yeah, 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 sure, yeah, sure. So let's take a rectangular one. If this is my feasible region, and I want to find the function f of x is x plus y, or let's take a 1D problem, then it will be even easier. Let's say I have a function. This is f of x, and this is my x, and f of x is something like this. Now I want to find the minimum value subjected to the condition. This is say 1 and this is say 2. So 1 less than or equal to, so let me put it in the same formula. So here I'll have one constraint is x less than or equal to 2 and minus x, or sorry, x minus 2 less than or equal to 0, and x greater than or equal to 1, I can write it as 1 minus x less than or equal to 0. So these are my inequality constraints. And I can have one more constraint saying that okay, first let's do the inequality, then I'll put inequality, then it will become very clear. Now we want to minimize this function subjected to these two constraints. So what I'm saying now is, if I scale both of these constraints with say some constant 2, some positive constant 2, then still this constraint, this bounds will remain the same. But I can multiply my objective function. Say the objective function is here y equal to, this is say some ax square plus bx plus c. My x values are not changing. All I'm doing is multiplying this entire objective function with some constant, 3 or something. Since this is a positive constant, the minimum value of wherever the minimum occurs for this function, it will be the same value for here, this one also. It will just be scaled by 3. So the optimal value will not change. So if this is the optimal value x star, this is not going to change just when I multiply these bounds with some constants. Now, however, now let's say we have an equality constraint also. The equality constraint goes something like x equal to 3 or x equal to say 1.5 or 1.2 or something. So if I have an inequality constraint x minus 1.2 equal to 0, this is my equality constraint and I multiply it with some constant. Still, the line will remain the same if I draw it on the graph. This is still the same constant, x equal to 1.2 will remain the same, whatever constant I multiply with, as long as this is a non-zero constant. When I put a 0, then it can have two possible combinations, like either this can be 0 or this can be 0. But that is not the physical constant. The physical constant states that h of x should be 0, which means this should not be 0. Only in that case, what will happen is you will end up having the same constraint as this. So in this case, what will be the optimal value? There is only one possible combination. You cannot vary x here and there. X has to be 1.2, so this will be my optimal value. And this is not going to change. Even if I multiply with 2, 3 or whatever number, as long as it is not 0, the optimal value will still remain the same, 1.2. But my objective function will change. Because when I substitute that, this is a square, a into 1.2 square plus b into 1.2 plus c. But here it will be 3 times the same value. So the objective function will change. It will be multiplied by that scalar. But then the extra value will remain the same. Understood? Yeah. Now this is with scalar multiplication. The next transformation is a one-to-one transformation. So what we are doing here, we are coming up with a new function phi, mapping from Rn to R, such that phi of z equal to x. Sorry, Rn to Rn. So we have phi of z equal to x, and we are saying one-to-one, so you can always do the inverse. Get z is equal to phi inverse of x. Now when we do this kind of transformation, again, what we are doing here previously, when we have the original problem, we are searching in the space of x, but now we are searching in z space. Like previously, if I want to do, I'll have to do for x1, x2 several different values, get f of x1, f of x2 and so on, and then solve and then see which of them is minimum, and that will give me the optimal value. But now what we are doing, instead of searching from different x combinations, I'll try different z combinations. So my search space has changed. Now coming to the objective value, like this is a one-to-one function. So if once I know the z value, I can always calculate the x value. So if I calculated z star, I can get x star equal to phi of z star, and once I get x star, I can substitute in the same function. The objective function has not changed. So the objective value will remain the same, but the optimal value will be different, and they are and now we know how to relate these two things. If we know one optimal, we can always calculate the other one, provided the function phi is a one-to-one mapping. Their inverse should exist for that function. Now you can have some functions which do not have, like it can be a many to one function. In those scenarios, what we have to do is ensure that this relation always holds. So what we do is put one more additional constraint and then put one more additional variable. So instead of searching just over x, we will search over x and z, and then we also add an extra constraint. Like all of these are the same way of saying that, like you have to satisfy the constraint gi of x less than or equal to 0, you have to satisfy hj of x equal to 0, and you have to minimize f of x. But then what we are doing now, we are just saying, okay, let me add one more variable z and say x equal to phi of z. And this is equivalent to the same problem as we have before. So just by adding one more variable and then with an extra constraint, nothing is going to change. Your optimal value will remain the same. Your objective function value will also remain the same, as long as this function is a one-to-one function. So this is like you are adding new variables. Like the previously the problem was only one variable, but now you kind of increase the complexity of the problem by adding one more variable set. This can be useful sometimes. We will see examples in coming weeks in linear programming and stuff. By adding new variables can be sometimes helpful. But for now, take it that both are equivalent. Yeah. No, no. I and j are just the number of constraints. It has nothing to do with x and y. X belongs to Rn. So if it is n equals to 2, then it will be x and y. X is always a vector. Whenever I write here x is a vector. And this I and j are the number of constraints. So for example, if you have a domain like a circle, you have only one constraint, but you can have some complicated domain, something like this. Then I need to have all these lines, each and every line, right? Equation of each and every line. So this is I equal to 1, this is I equal to 2, I equal to 3, I equal to 4, I equal to 5, I equal to 6, like that. So that is I. And I can have equality constraints. If I have equality constraints also, like here I'm just taking the entire domain, so all of them are inequality constraints. But if I have equality constraints, then they will be j. J will also vary from 1 to p. So if m is basically the number of inequality constraints, then p is the number of equality constraints. Yeah, j is also the same. So you can have different equality constraints. So for example, in a physical problem, so you're from which background? Which like you're from engineering background, right? I think you told that. You're from mechanical. Okay, so if you have a CFD problem, for example, so in a CFD problem, what are the different kinds of constraints? Say you have to satisfy continuity, for example. Del dot u, sorry, you have to satisfy the continuity equation. That is one constraint. You have to satisfy the momentum equation, x momentum equation. That is j equal to 2. Y momentum j equal to 3. Z momentum j equal to 3. Sorry, j equal to 4. So on. So each of those things are equalities that you have to satisfy. They will form. Yeah, yeah. It represents different functions that have to be satisfied. This is like the entropy thing. Like if you pose it as an inequality, this is entropy kind of thing, and these are the kind of mass, momentum, energy kind of thing that have to be conserved. And your objective will be something like say minimize drag or something. Yeah. Yes. Now that is another constraint, but you can see here, right? I can. This is also basically an equality constraint. So I can always put this x and z combined together, put one variable y, and then write it as minimize f of y subject to gi of y less than equal to 0, some hg of y equal to 0. This can be put inside this one, right? If I can club both an x and z into one vector. So for example, if you take the same momentum equation, what I can do is, so say instead of writing x, y, and z momentum separately, I'll just put u as a vector. Then all I have to do is write only one equation for momentum, right? In vector form. So this equation will then be written in a vector form. So here instead of 1, 0, you'll have multiple zeros in some, like you write it as a matrix. That's it. Okay. So, but for now we'll stick to this normal notation, like individual element wise we'll stick. But for each of these equation will again depend on the entire vector, not just one of them. Like your momentum will depend on u, v, and w, right? Each x momentum will depend on u, v, w. Y will depend on u, v, w. Z will also depend on u, v, w. So this x is a vector. This input to the function is a vector, but the function itself is a scalar. It's like hj is a function that maps from R into R. That part is clear, right? It's like momentum vector, momentum equation, x momentum will give you only one value, but then it will take as input the entire velocity vector. Yeah. So similarly for GI also. GI also takes an n-dimensional vector as input and gives you only a scalar output. When you take multiple GIs and put it as a G, something like G1, G2, and all of them, then it will be a vector. Similarly for H, it will be HP, something like that. So this M is this M, this P is this P. Okay. No, no, we are just writing it as a matrix. It is not a vector in a physical sense. This is like just putting all the equations together. Okay. Okay. Yeah. So this is one-to-one transformation. The next one is a monotone transformation. In this, what we do is we take the original function and then we take a monotone function. Monotone function is essentially we assume several functions, psi0, psi1, so on. All of them are monotonously, like psi0 is a monotonously increasing function. So which means if f of x is increasing, then psi also will increase. Similarly, if it decreases, other one will also decreases. So whenever f is minimum, at the same time the psi naught of f. So I'm representing f tilde with psi naught of f. This will also be minimized at the same point. Wherever this attains the minimum, this will also attain the minimum at the same point. In a similar way, we transform the inequality and equality constraints also, such that gi tilde is psi I of gi, but we have additional constraints on this. Now we have to recover the same gi as we have before. So what we do is we put this additional constraint that psi I of u less than or equal to 0, where u is essentially your g of x. So what I'm saying is when I'm saying u less than or equal to 0, that this means g of x less than or equal to 0, which is always there. So I can get back to my original formulation. Same way I will define for the other one also. Psi m of u equal to 0 implies u equal to 0. So u is basically my HA of x in this particular case. So I'm getting back my original condition. So this is also equivalent to whatever we have before. So your feasible region will remain the same, but the function value will be different because you are using a different function here. The value will be different, but the point at which that value is obtained will always remain the same as long as this is a monotonously increasing function. That is the important point over here. Monotonous is something like this. It keeps on changing, it keeps on increasing or keeps on decreasing. Its derivative is like it will not be zero anywhere. Monotonous is like it keeps going on. Yeah. So yeah, that is important because if you have some at some points where something is zero, something like this, then you may not be sure whether the minimum is here or somewhere. You cannot say for sure. But now if you know that it is continuously increasing or continuously increasing, then wherever f is minimum, psi naught has to be minimum there. Because if f is little higher, then psi naught will also be higher at that particular point compared to the previous point because it is an increasing function. So to ensure that f and f tilde have the same minima, I need to have the constraint that psi 0 is an monotonously increasing function. It's a function of function value. You take x value, from that you calculate f of x, and from there you calculate psi naught of f. You can write something like this. It is just saying that there is, yeah, this, yeah, you can take as, for example, the energy equation or something. In say for example, you're familiar with PCA concept, so basically energy is expressed in terms of variance or something. Or you can take even just take the example of energy. So you can what energy is basically, let's say kinetic energy, half mv square or something. Let's take half u square, like per unit mass. So this is your thing. I can write it this as what? This is a function. I can take f as my u. I can take my psi 0 as x square. Then psi 0 of f will be what? It will be u square, right? So this particular transformation by psi naught equal to x square, this particular function is a monotonously increasing function. Oh, no, 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 double differentiation. So this function is monotone because x square keeps on increasing. With respect to differentiation, we can't say things like that, right? So energy kind of things usually will be energy or variance kind of things will usually be something of this sort. Maybe yes. So this is basically like to identify if you already have something like this. So for example, if you take this problem, instead of minimizing u square, you can always minimize u. If your u is minimized, then you're pretty sure u square is also minimized, right? So all we are trying to say is these two problems are equivalent. But which problem to solve again comes like depending on your algorithm. Some might work for some, like some may be computationally cheaper than others depending on particular cases. How to do that, and that will come later. But for now, what we are saying is both are equivalent. You either minimize this or minimize this, you will end up with the same answer. Okay. So the next transformation is the slack variables. This proves very useful when we start linear programming. I think that will start in maybe a couple of weeks. So here again, as we said before, we have the inequality constraint GA of x less than or equal to 0. That constraint we are modifying like this. We are adding extra variable SI equal plus GA. So we have GA of x less than or equal to 0. So all I can do is I can add some constant x, some positive constant to make it equal to 0. So this is some positive quantity. So when I add the positive quantity to a negative quantity, so that it will be 0. Now I will have, previously I just have x as a variable. Now I have extra variable, this SI. All these SI will be my extra variables. And additionally, the inequality constraint is now converted to an equality constraint. So now what will happen is this will be my new inequality constraint and this will be my set of equality constraints. So again, it's the same thing. You have the problem with minimize some objective function, but my search space has like the domain is changed. Previously it was just x. Now some new variables are added. These are my equality constraints and these are my inequality constraints. The main advantage that we get here is the GI of x previously less than or equal to 0 or all the inequality constraints whatever we have or some functions of GI, but now all of them are just a very simple inequality constraint. They just say that it has to be positive. How to get advantage of this, like how to exploit this particular factor, is again we'll see something when linear programming comes. For now, it's sufficient to understand that just by doing this transformation, we converted some of the inequality constraints into some simple form that can be used to our advantage a little later, so that we have more equality constraints than inequality constraints. Because we already know methods. For whenever we have equality constraints, we know how to solve the objective problem. So that we discussed in the last week. We can use implicit function theorem when we have equality constraints, and we can always write this del x of f plus, so we discuss the concept of Lagrange multiplier plus whatever inequality constraints we have equal to 0 sigma, and we can solve this whenever we have equality constraints. So this inequality, how to deal with this, we'll discuss a little later. But for now, let's assume we do not have this inequality. Like assume that in the way that you formulated, this will always be positive. Then you just have equality constraints. Then you can just use the Lagrange multiplier concept, and then you can find your optimal values. You can find your lambdas. You can find your x. So this is essentially like you have more better methods to deal equalities than inequalities. So we'll convert them into equalities and use the already existing methods for equalities and solve them. The main point here is your objective function, the values of x star that you get will remain the same, and your objective will also remain the same. So this kind of transformation will not change any of these. So you can either use, you can convert the original problem to this problem and solve this problem, with then the original problem is also solved. All the transformations are similar in the same way. So if you solve this small problem, the original problem will remain solved, or the other way around. Solve one of them, the other one is there. The next type of constraints are the linear equality constraints. So if you see here, the original problem versus this problem, you do not see the HG of x equal to 0 equal to that particular kind of constraint here. So this is exactly the one that we see in case of the implicit function theorem also. So we have an equality constraint. What we can do is always convert the equality constraint, reduce the variables, and then substitute back in the objective function so that my space is reduced. And then I don't have to specify the equality constraint again. So for example, if you have some constraint like x plus y equal to 1, and then you have a function of f of xy, I can always convert this function. I can substitute y is 1 minus x. Then this entire thing will be a function of x only. And then previously, if I have to write the problem, then it will be something like minimize f of xy subjected to the constraint h of xy equal to 0, where this is x plus y minus 1 equal to 0. Now the new problem will be you just write minimize f of x. There is no equality constraint here. The inequality constraints will remain the same, but then they will be transformed now, so that whatever variables are there in this f, like whatever variables you replace. For example, here I changed my y equal to 1 minus x. So I converted y in terms of x. So in that case, in my inequality constraints, I should not have y. So this is the transformation that will remove the y. So all these things will live in terms of x. And then you can write only those constraints, and you will effectively solve only this problem. This is also kind of a little, all you're doing is rearranging the equations and then doing that simplification, like substituting those in the original value so that your your dimension gets reduced. So instead of searching in n space, you are now reduced it to whatever the variables that you can reduce. So previously, if the domain was x belongs to Rn, which means I have n variables to find, and I have p constraints. So what I can do is I can rearrange these variables and reduce it to n minus p. So if it is R3 and I have one constraint, then I can reduce it from 3 minus 1, so that is 2D problem. So a 3D problem, which was originally a 3D problem, has now been converted to a 2D problem. So the number of unknowns will get reduced, so it might become easier to solve sometimes. Main point here is your optimal value that you can encounter is not going to change by this transformation, and your objective function is also not going to change. Yeah. So this is with respect to transformations. There is one more thing that is discussed in the lecture video. I did not include this here. That is when you have two or how do you optimize two or more functions? But that is not necessary for the assignment now. So I've kind of excluded it from this session. So if you can record, you can watch the videos, and if you have any doubts, we can discuss that as well. The next part is on convex analysis. Mostly discusses on the definitions only. So I'll stick to this for this week, and the next week we will see more problems on this. The first one is the concept of you have two different points in R, let's say, and this is a line joining both of them, the line segment. Why I'm calling it a line segment is because of this particular domain. I'm saying alpha is restricted to 0, 1. So I have 2 points, x comma y, and I can have a line this. I can represent any point on this line P using this relation. But whenever I say alpha belongs to 0 comma 1, it means it only represents, it will be restricted to this point. This point P cannot go outside, or P prime, let's say P prime. P prime will be in this as long as alpha is 0 to 1. So then we call it a line segment. With this definition, we say set S is an affine as long as if the line, again, underline on this, this is a line and not a line segment. If the line passing through any two distinct points of S lies in S, it should be the entire line, not just this line segment. Take any 2 points, draw a line which spans the entire space, and then if that line also lies on S, then you call that particular set as an affine set. Classic example is a plane. If you take a plane, take any 2 points on the plane, draw a line through them. It's like if you take this particular screen that whatever I'm showing here, take 2 points on this thing. Both are present on the screen itself. So when I join them with a line, that line will also lie on the plane itself. So this plane is an affine set. The line, again, the same definition as I said. If it only belongs to 0 comma 1, then it is a line segment. If it belongs to R, then it is a line. If a particular set is affine, then any affine combination of points in S will also lie in S. Or it's a kind of if and if, like a necessary and a sufficient condition. Affine combination is basically, or like you take something like this. So if you have point xi, this is called affine combination. Okay, belongs to R. Just take the weight summation of all the points, and when you do the weight summation, whatever point you get is still going to lie in the point. So if you have, say, a triangle something like this, 3 points in R2, I can take a weight combination of these points. If, for example, if you have the weight to be 1 by 3, then it will be centroid. If the weight is something else, you will end up with some other point. Depending on whatever weights you take, you can end up and span the entire space. So all these whatever points you can get by varying these weights, all those points should also lie in the same set. The set here is the entire plane. And whenever you do this weight combination, you're not going to go into the 3D space. So if it is in XY domain, whatever combination you do, you're not going to end up with having a non-zero Z, like Z value is 0 here. Any combination you do here will end up giving you a Z value 0 only. So all of them will lie on the same plane. So this is also an affine set. So an affine set it's a necessary and sufficient condition. All the affine combinations of the elements inside the affine set will give you an affine set only. The next is with respect to intersection. If you intersect any number of affine sets, that is going to be an affine set. For the triangle, yeah, if my triangle coordinates are, say, something like this, some coordinates, I'm saying all those coordinates are lying on xy plane, which means Z will be 0. Yeah, it will be 0 automatically. So whatever you multiply, the 0 is not going to change. So it will still remain on the plane. Yeah. Yeah. So the next concept is an affine hull. Affine hull is basically the smallest affine set containing whatever your objective is. So if you want to enclose this with an affine set, or like you can have a high dimensional problem, and then you want to understand, dimension is basically the number of independent things with which you can describe that particular set. Then affine hull is one of the smallest set that can describe the entire number of elements in your case. We will take an example of this once we start solving problems. But for now, it's sufficient to understand that this is the smallest kind of a wrapper. You have some chocolate or something. If you want to wrap it in some cover, the smallest cover that you can always wrap it with leaving enough space, or how much ever space you want. But then the smallest wrapper that you can wrap the entire chocolate in is your affine hull. So that will kind of tell you what the dimension of the chocolate is. Here, it's basically the dimension of the set is, whatever your feasible space is. So what I'm trying to say is you have a certain number of feasible points. So that, for example, you have a chocolate that you want to wrap around. All the points on the chocolate is your feasible domain. So now I want to find the dimension of this. I want to find the dimension of the chocolate. So what I have to do is I'll enclose it in a wrapper. The wrapper dimension will be my chocolate dimension. So that wrapper, whatever I'm enclosing, like how do I ensure that it is completely enclosed is, for example, if you have a 2D plane, let's say your chocolate is very thin, like let's say your chocolate is something like this, very thin wafer kind of thing. If it is a very thin wafer kind of chocolate, if I want to, I can always enclose it with something like this. very big box to make it 3D kind of thing. But that won't overestimate the size of the chocolate, right? So FN hull is basically the one that will enclose the chocolate perfectly fine. So only the wafer will be enclosed, and the third dimension, the depth is near almost zero. Whatever the wafer thickness, it should be that thickness. The definition is like we are defining it as the smallest possible affine set. You can always wrap it in a bigger ones, but the smallest one, however small you can go with enclosing all the elements of your desired set. And this is just indirectly defining that this is the minimum thickness of that particular thing is. So that will give you the dimension of it, right? Yeah. How to calculate it for a given number of points is something that we will see once we have the other definition. There are other examples also. You can all say, for example, you have the example that I can think of is, say, for example, you have something like something like this. Like rectangle is a very straightforward one. Let's say I have something like this, some shape like this. Now I want to enclose this shape and find the dimension of this shape. But then I cannot. I can do it in different ways. One way is just take lines like this. I can enclose with lines like this. Like if I know that my plane is an affine set, so this is basically a plane in the third dimension. So it's like a plane. It becomes a line when I draw it on this curve. But in the third dimension, you can imagine it like a paper perpendicular to the screen that you are seeing. And this is when it is cut on this plane, you will only get a line. So I can take several such lines, and this is the minimum I can get it to enclose this entire surface. So this will be my affine hull. And the size of this affine hull, so maybe you can take the area under this, and that will give you an indication of how much the size of the object is. It's basically that. I'm just giving you a simple example. Like if you have just like I'm saying, it needs to be an affine set, right? Plane is an example of an affine set. So if you take planes, then this is the smallest possible affine hull you can make with the planes. If you want to take a curved surface, and the problem will be if you have a curved plane, like a curved surface, like you take coffee cup or something. When you have a coffee cup, if you have something like this, just the elements on the coffee cup are your affine set. Do you think the elements on the coffee cup are affine set? So this is my U-shaped coffee cup, and I'm saying I'm defining my set as all the points lying on this cup. Will that be an affine set? Okay, so if I consider one point here and another point here, and I take a linear and I draw a line through them, when I take a weight combination, then the point falls outside the cup, right? Yeah, so then I cannot call this an affine set. But if when I have yeah, you got it right. Yeah, so when I have a plane, I can consider always it as an FN one. Okay, I don't know gradient. I didn't get you. I didn't get you. I haven't talked about gradient anywhere. I didn't get your question. So which one is nonlinear? You are saying the cup is nonlinear? Okay. Okay, this one. Yeah, for this particular space, this is a nonlinear one. So if, when you have these surface surfaces, the maximum you can get is only this. You can't go beyond that, right? So this is the smallest possible one. So this is my affine hull. That was what I was trying to say. You cannot match exactly. That's why we are saying the smallest possible one. You won't get the entire thing, but if this is the smallest possible one, then that is the dimension of that particular set. Yeah, it will have some. It's same like if you do meshing. We want to refine some very fine mesh. All we can do is within some accuracy we can get it. Of course, you can always, instead of doing this, you can always split this, right? Like instead of considering one big line, you can always consider some small lines, cut, and then approximate it. But we are restricting, like in the sense that okay, this is enough. You can always maybe take one more line like this, another line like this, and then take an intersection of all of them. eventually, like as n goes to infinity, it might match, but we are not going to that. We will discuss that also. We will discuss that as well when this actually approaches that. Maybe not now. Once the linear programming, not even linear programming. After that, maybe eighth or ninth week. This is basically saying if this is one point and this is another point, when you take alpha x plus 1 minus alpha y, you will get a new point. So yeah, it is only one dimension. This is just one dimension. So you have one point x here, one point y here. So all I'm doing is alpha x plus 1 minus alpha y will give me some new point. Depending on alpha, it can be anywhere on this line, on the x axis. Yeah, y represents another point in R1. It's not R2. Yeah. The next concept is relative interior. So this is useful essentially when we have, for example, if you want to identify certain domain, but we said that we have the constraints like GA of x less than or equal to 0. This represents the interior of your domain. But now you can have, whenever you add new variables, then the dimension will increase. You might originally have a 1D problem like this, 1D problem, but then I can always introduce a new variable. As we discussed in slack variable concept, you can always add new variable and still make the optimization problem same. But then when you add the new variable, for example, if you see this here, if for now let's say x belongs to C, there exists an r greater than 0 such that b of x, let's for now let's say this is not there. A subset of C is what my desired set is. So what happens when you consider a ball of radius r? When you go to higher dimensions, all the new points, all the points inside the original domain will not be there. For example, if you have this, let's say this is my y-axis, like I added an extra dimension. Let's say z is my extra dimension that I've added. So what will happen now is my feasible domain is still the same. Only this, whatever is in this domain is my feasible domain. But now if I consider a ball at point, say some point here, in 2D, if I consider a ball in 2D, it's basically a circle. If I consider a circle like this, then it should the circle has all the points. It has points here also. It has points here also, and it has points on x-axis also. But my feasible domain is only x-axis. But by this definition, these there exists an r greater than 0. There, like, which means there should exist at least some finite radius r. Which, as long as the radius is finite, then you will always have points from the other dimension which are not in my feasible domain. So this will be a null set. Like you cannot find an r, which means the interior will be null. So in order to avoid that, we are saying that intersection of this as well as the affine hull. When we take the affine hull of C, then it, as I just defined, this is like a wafer you have of chocolate. Then the affine hull will be a infinitely small thin layer on top of it. When I take the intersection of this ball with the affine hull, then all I'm getting is just this slice. So which means the relative interior is the same. So this is just the extra additional kind of a technical detail, but physically it's of not much significance for us. All we can do is when we added an extra dimension, our feasible domain is still remaining the same. It's just a kind of technical way of saying that. But I think that kind of comes obviously also. Just by adding new variables, you're not going to change your feasible domain. That should remain the same. If you're changing it, then your problem itself has changed. Which should not happen. Which is which should not happen, right? So physically, you just have say momentum, mass, whatever these are, they are the physical constraint. If I add a new variable, some efficiency or something, or not efficiency. Let's say I have u, v, w, and then let's say temperature. These are my variables. I can always add a new variable, but that new variable shouldn't change the physics. No, nothing like that. It's just that if you consider a ball or something, it will have all the directions in it. If you consider a triangle or something, then it has the corners. Because of the corners, it will get a little complicated. But if you have this, you can take unit vector in any direction, and all directions will be included in it. So when we can simply say r greater than 0, it means from any direction you can go. You don't have to worry about direction. Yeah. Yeah, this is with respect to affine sets and affine hulls. The next one is the convex set. So a particular set is called convex, the same definition as affine set. The only difference here is your alpha should be 0 to 1. In the affine set, our alpha can be r. But here we restricting it to saying that alpha should be 0 to 1. So alpha x plus 1 minus alpha y should be a line segment. So then we call that particular set to be a convex set. Yeah. Again, the difference is just with respect to alpha. The next definition is a cone. You call a particular set cone if you take each and every element from the particular set and scale it with a, this is a non-zero, non-negative lambda, non-negative scalar. When you multiply it with a non-negative scalar and get that new element, and that new element, if that new element also belongs to S, then you call the particular set as a cone. It's just like the physical cone. If you have a cone, if you have something like this cone, you can take any element in this cone, and this is my origin. If you join this to this vector, when I scale this vector, it will only become a new vector, and that new vector will also be a subset, will also be a set of, will also belong to the same set. Such kind of sets are called cones. Again, for now, like all these definitions will be useful later. Just bear with me that I'm not explaining the significance now, but just stick to the definitions for now. How these definitions will be used to solve our optimization problem, we'll see them in coming weeks. And by this definition, it should always have an origin. So x equal to 0, lambda x will also be 0, lambda times 0 is also 0, so that will also belong to the same set. So whenever we have a cone, origin should always be there in the cone. And the next thing is cones may not always be convex. So just because you have a cone doesn't mean it will be convex. So for example, let's take coordinate axis, xy coordinate axis. These are my axes. My cone is basically any point if I take on the axis. Let's take this point. If I scale this point, it will become a new point, lambda x1. But lambda x1 also belongs to the same set. It is also lying on the coordinate axis only. So this is still a cone. I can take any point here, scale it down. Say this is y1. I can scale it down as well. That particular point also lies on the y-axis. So any point I can take on the axis, I can always scale it and again bring it back on the axis only. So this will be a cone, but then it is not a convex set, because if you take these 2 points x1 and y1, the linear combination alpha x plus 1 minus alpha y should give me a line. Depending on the value of alpha, it will be somewhere here, whatever alpha value you choose. So this is not belonging to axis. So it is not a convex set. Like, it may be convex, but it is not guaranteed that a cone will always be convex. The next one is the concept of hyperplane. Yeah. Next. Yeah. To include origin, just put lambda equal to 0 is also fine. And this has to be finite, right? I can't just put something like this, because infinity is just an indication to say that nothing beyond it exists. So I can't close it. Yeah. The next one is the definition of an hyperplane. This is just like a normal plane. When you have a plane equation, say ax plus by plus z in 3D, this is the equation we use. All we are doing is just writing it some in n dimension. If you write this in 4D or 4 dimension or 5 dimension, all we are doing is we are just taking all these things, this entire thing I'm calling a transpose. This entire thing is my high dimension x, and this is my b. This is just like a normal plane, but just in higher dimension. All this means is you have a set of linear equations. Now, if you see, the next one is when I say a transpose x equal to b, I can always write it as a transpose x minus x naught equal to 0 if a transpose x naught equal to b. That is also, you can see it directly from here. So this a transpose is basically like in your 3D, if you compare this, so you can always write this as a into x minus x naught plus b into y minus y naught and c into z minus z naught. If you recall how we derived this, so if you have a plane equation, so you have a plane with some point x naught, y naught, z naught. What we do is we have the normal vector. This normal vector is a cap plus bj cap plus ck cap. Then we take some arbitrary point x, y, z. We join these 2 points. So that vector will be x minus x naught, y minus y naught, and z minus z naught. And this is the normal vector. Since they have to be perpendicular, the normal vector times this particular vector should be 0. That is how we derive the plane equation. The same thing, just in arbitrary dimension. We call it as a hyperplane. Now, half space is again is very similar. You can draw parallels here. In 2D, you can say like this is my line, for example. This is x plus y equal to 1. As long as I'm the line, it is x plus y equal to 1. But it extends in both the directions. Now, when I say it is less than or equal to 1, it means the entire region, This entire region will be x plus y less than or equal to 1. That is basically we are calling it a half space because it's just dividing it into two halves. No, not equal halves, but essentially dividing it into half. This entire thing is excluded and the entire thing is included. So that's your half space. Now you can have several half spaces, and if you take a finite number of those half spaces and then take an intersection of them, then it will be a polyhedron. So in 2D, I can have several lines. Each line is a half space because it can be represented in this form. Instead of this, you'll have some x and y. Like this x it will be replaced with x and y. This will be some constants, a1 and a2. This will be some intercept that you have. I can take several number of such lines and then do an intersection of all those things. So this will be my intersection. So this will be my polyhedron. Intersection of this finite number of half spaces is a polyhedron. Okay, maybe now, so is circle a polyhedron? Yes. If you draw a line and we are saying less than or equal to b, it means only this part of the line, this part is considered, the other part is excluded. Okay. Yeah. So is circle a polyhedron? Yeah. So this is not a polyhedron because we need a finite number. In order to represent a circle, you would need infinite number of tangents, so it is not a polyhedron. The next one is a bounded polyhedron. A bounded polyhedron is called a polytope. So this example, if you see, here you just have one of them. So, but this is spanning across entire half space. So the entire region is included. So these kind of things are not bounded. So this keeps on going in this direction. So that is not a polytope. But for example, if in this half space, if I also include x-axis and y-axis, so if I include x-axis, y-axis, and this line, if all three of them are included, then it is bounded. That is what we call a polytope. So this is exactly the kind of thing that we will see in, with the introduction of slack variables. This is what happens when we introduce slack variables. You're essentially adding two extra half spaces, so you'll have a bounded problem, and it will be much easier to solve it. We'll see its advantages in linear programming. Again, a hyperplane is always a polyhedron. The way we've defined it, this is an equality and this is an inequality, and inequality always has equality in it. So this is a hyperplane will always be a polyhedron. That is just by the definition. Yeah, yeah. Before going to problems, yeah, yes. This is just a special case of it, right? This is just a special case, which which will be used like when you solve some problems. Equality is much easier to solve than inequality. Inequality means equality can be there or cannot be there. But when it happens, there are some easier ways and tricks to solve. That's why we specified it separately. Yeah, no other. It's like your momentum or whatever conservation of mass or something. This has always to be satisfied. Yeah. Hmm. Slack variable is essentially this S. Okay. If you recall thermodynamics, like the entropy concept. So when we have the third law, what we say is delta S for the total universe should always be positive, right? Or sorry, should always be, or let me put it this way. Your entropy for a closed system, if you have, it should always be zero. But then when we say there are irreversibilities, then your entropy should always decrease or something like this. You have del Q by T less than or equal to zero for an irreversible process. Remember this. So what did we do then? We take the same thing and then we add an extra thing called delta S gen and we set equal to zero. This is what we do in the relation, right? And then we put the extra constraint that delta S gen should always be positive. Like it will be equal to zero only if it is a reversible process, but otherwise it is greater than if there is any reversibility, then it will be strictly greater than zero. So this delta Sn is your slack variable here. So this is my original inequality constraint, ga of x less than or equal to zero. But the moment I add delta Sn, that is my slack variable here. with the constraint saying that it is strictly positive, or depending on whatever it slack variable. Now again, you can see here it is strictly greater than 0, or it can be equal to 0 depending on the type of process, right? The same thing will come up here also. So the inequality constraint can have two different natures. It can be strictly less than 0, or it can be equal to 0. So like if it is irreversible, then you call it like when it is strictly equal to 0, then we call it as an active constraint. Okay, we'll get to that later, but for now there is a difference. Like equality is different from inequality physically as well as here also. Okay. Hmm. Hmm. This is essentially resubstituting. So when you have, let's take the problem you remember last week when we solved, you have some function f of xy, and we have a constant x plus y equal to 1. So instead of saying it as a 2D problem, I can use this equality, convert y in terms of x. So it becomes from a 2D to 1D problem. Yes. So what we are doing here is this is just a transformation to do that. So z, I'm searching over z. Z will be in lower dimension. So this f will convert from lower dimension to higher dimension. And this is possible only when you have this linear equality constraint, because when you have linear equality constraint, I can always write them as ax equal to b. When I write it as ax equal to b, then I'll have some null space az equal to 0. I can rearrange, like a is not a square matrix, it's a rectangle matrix. So when you have a rectangle matrix, you can always choose certain linear independent rows, only choose those columns and make everything else equal to 0. Then your number of variables is reduced, so you can solve it. Only with a linear problem. Non-linearity becomes complicated. Yeah. Okay. So if there are no other questions, then we can solve some problems now. There any other questions? Okay, then we'll take problems. These are again straightforward problems. So maybe you can take a couple of minutes to solve and let me know the answer. The first one is straightforward. So we have some function f of z equal to z square e power minus 5z. You have to find the maximum value of it, z star value. What is the optimal value of z that maximizes this function? The first thing. So how do I approach this? So it's a maximization problem subjected to one inequality constraint that z is strictly positive. So what condition can I use here? So I didn't say anything about the feasible domain. It says z belongs to R. It's a 1D problem, let's say. So in that particular case, the first thing we have to see is z belongs to R is an open set. So this is an open set. And the next thing I have to check is whether this function is continuous and differentiable. Okay, differentiable, it is continuous and it is differentiable. So you have an open set, you have continuous and differentiability. So I can always use the first order optimality condition and then say z star should be 0. And then in order to have the maximization thing, I have to put the second order condition to be less than 0. And both of these have to be satisfied provided z star is greater than 0. Like you can have multiple values of z star. For now, we will solve it in a brute force way. So we will find all values of z star and take only positive values and see whether you are satisfying this constraint. How to include this directly in the problem, we'll see that later. Okay, you can quickly tell me what is the value of z star you're getting. Okay, this is pretty straightforward. You have only two possible values, and this cannot be used because of this constraint. So this should be my solution. This is a straightforward problem, not much. Just skipping this. I don't think that requires much discussion. Okay, this is something you can try out. To have two points, the 5, 3 and 6, 4. Which of the following is a convex combination of x and y? So how do I know if it is a convex combination of x, y? So convex combination, if I denote it with, let's say convex combination is basically How did we define it? It's just a linear combination, sigma alpha I xi, whatever number of variables that I can consider in the, whatever number of points I have. So here I have 2 points. So this will be something like alpha 1 times 5 comma 3 plus alpha 2 6 comma 4. So this will be 1 point. This will be the other point. So out of these points, you have to check this. So you have two variables, 2 unknowns. I can solve, get the values of alpha and alpha 2. What is the catch here? What did I miss here? How do I know which of these is convex combination, which is not? Is the question clear? Yeah, okay, no problem. Yeah, if you recollect, extra constraint that needs to be satisfied for convex is you need to have alpha to be between 0 comma 1. In affine set, we don't need this constraint. Alpha is just be any real number, it works out. But for a convex combination, this is extra constraint that needs to be satisfied. Whatever this alpha 1 alpha 2 are, they should be between 0 comma 1. That is extra constraint that you have to ensure. Now you can check with each of these points and tell me what whether they're satisfying or not. For example, if you take first solution, it goes something like 4 equals to this and 0.5 is. I think we also got the same answer when I solve. I'm getting alpha 1 as something like this. This has 2.75 or something, which means this cannot satisfy that. Can keep doing for the other ones as well. Maybe you can solve the last one. Tell me if it matches. I don't know. I have to check. So what is the value of alpha 1 and alpha 2 you got for the last one? Yeah, 0.75 and -1. Okay, then they are not satisfying. Then I note this. Okay. Okay. The next problem is okay. Well, is the convex set an affine set? Is it always true? Okay. Any example? So a coffee cup is an affine convex set. So it's not a convex set, right? So yeah, the question is a convex set is affine. Sorry. Yes. Multiple. See, okay, if you have a line like this, let's say we take x-axis. So that is an affine set. So can I consider x-axis as a convex set? Yeah. So the question is like every convex set, will it be affine set? Or let me put it another way. I have a set which is affine. So if a set is affine, can it be convex always? That is clear, right? So if I have an affine set, can it be always convex? So in the not necessarily that you can say right from the definition. So when we have the definition, we wrote it as alpha x plus 1 minus alpha y. So if you have x comma y are 2 points of this set, this should also belong to the same set, but alpha belongs to R. If alpha belongs to R, then we are calling it an affine. But if alpha belongs to only 0 comma 1, then we are calling it convex, right? So if a set is an affine, it means alpha belongs to R, which means alpha can be 2, 3, whatever. If any of these are there, then it cannot be convex. So I think so. It should be like if I think I should have asked the question in this way instead of this. So an affine set doesn't mean you will always have a convex set. Okay. The next one is union. Union of two convex sets is convex. True or false? We discussed about intersection. Intersection of convex sets is yeah. Intersection of convex is convex. Union is convex is also convex. Okay. Let me give you an example. Let's take x-axis, but let's restrict to 0 to 1. This is one set. Everything in this set let us call S1. And let's say I have 2 to 3. This is S2. S1 is convex. Every element here, if I take any two elements and take a linear combination of them, it will also fall in the same set. So this is convex. S2 is also convex. When I take union of S1 and S2, which will include all these points and all these points. So is a union also an convex? So I can not like you can take this point and let's say this point and this point. Then whatever when I do the linear combination, it can fall outside the set, right? So it may not always be true. When you take an intersection, then it will always be a convex, but union will not always give you a convex. Okay. Okay. This is another one. So you have a set x denoted by this line x1 plus x2 equal to 10. Is this a convex set? If you just draw this, this is x1, this is x2, x1 plus x2 equal to 10 is something like this. It goes in all directions. It's a line, right? So it will go even beyond into second quadrant and fourth quadrant also. So is this particular set convex? The set of all points on this line? No. Why? No. Why? Yes. Anything? Yes. Okay, it is an affine set. This is affine. Okay. What about convexity? No. So why not here? So if it is this line, I can take 2 points here, and their linear combination will also lie on the same line, right? Yeah. So, or if you want to go it in mathematical ways, so all you have to do is take 2 points, take 2 arbitrary points, a comma b. This is point 1, and let's take point 2 as c comma d. A comma b are lying on first on that line, so a plus b should be 10. C comma d are also lying, so c plus d should also be 10. Now I have to take a linear combination of these 2 points, so that will be some alpha a comma b plus 1 minus alpha c comma d. That is something like alpha a plus alpha c and sorry alpha a plus 1 minus alpha c comma alpha b and 1 minus alpha d. Now if I substitute this in the equation, x1 plus x2 will be alpha into a plus b plus 1 minus alpha into c plus 2. So this is alpha into 10 plus 1 minus alpha into 10. That is just 10. So even the linear, when I do the linear combination, that is point P, P is also satisfying the governing equation. I mean, satisfying this particular equation. So P also lies on that line. So all wanted to show here is when you have these linear equality constraints, something of the form Ax equal to B. So this is, you can write it as Ax equal to B, something like an identity matrix times x1, x2. Okay, sorry. It is just one equation. So should write it as 1, 1 equal to 10, something like this. It can be written as Ax equal to B form. Whenever I can write it in this form, it will always represent some line or some hyperplane or something. So you see the hyperplane definition, that is basically when you write it as A transpose x equal to B. That is the definition of a hyperplane. So when you have these linear constraints, then it will become a hyperplane. And when you have an hyperplane is a convex set. So it will always be convex. No, half space is when you have inequality constraint. When you have equality, you call it hyperplane. Okay. Okay, now what about this set? Equality, it is clear. Equality, when you have equality and linear, it will be convex. That is clear because it represents a hyperplane. So what is this? Is this a is this a half space? No, but then you have to see the other part as well. So when we define a half space, we define it to be A transpose X less than or equal to B. It's not about equal to B, it's about this. This is a linear constraint. But here, if you have x square and x2 square, it's a nonlinear thing. No, it's not about grid. It's about this. It's a nonlinear one. So so you don't call it a half space. But always, this is basically some circle equation. So again, you can have those infinite number of tangents and then do something else. So basically, what we are trying to say now is when you have a constraint like this, if you want the entire problem to be linear, all you have to do is decompose this into infinite number of tangents and then make it linear. But ideally, we won't do infinite number of tangents. We will say that if you have a circle like this, maybe this resolution is sufficient. So you take say 5 or 6 tangents and then you mesh only with them. And then the problem will actually be converted into linear. Like this is what you do even in CFD, right? When you have say finite volume method, or what we are trying to do is we take the entire governing equation, we discretize into some elements, and within each element we'll assume some linear or something. So the entire problem will eventually get converted into a linear problem. It's a non-linear problem getting converted to linear problem, and then you solve it. Okay. Now what about this? Is this convex or okay? Forget about linear, non-linear. Is this convex? Okay. How do you say it is not convex? Okay. So you mean like whenever I have a non-linear, will it always be convex? Or sorry, will it always be non-convex, or can I have a convex set which is non-linear? Okay. So when you have some nonlinear thing, you have some curvatures. Then if I take 2 points and I take a linear combination, that point will may always lie outside, may always lie outside. So if it lies outside because of this curvature, it will eventually go outside. So if any one point lies outside the set, then it is not a convex set. Okay. Or you can also, instead of arguing this way, you can always start in the same way, like as before. You take 2 points A comma B, C comma D, and then substitute them and then verify whether this constraint will be satisfied or not. Anyway, it won't be satisfied, so eventually you'll come to the same conclusion. If you want, you can just satisfy that here. Or maybe I can show it directly on the graph. So this is basically the entire space, everything except the circle, since it is greater than or equal to 9. But the origin should be somewhere here. So if I take one point here and I take another point here and take a linear combination, that point will come here inside the circle, which means it is outside the set that I want. So it is not convex. Okay, well, how about this? This is in R2 and I have an equality, inequality, but linear constraint, linear inequality constraint. So which of these is true for this? Let's go one. Can I call it this as cone? This will be some line like this. Say this is x1, this is x2, some points here. So can I call this particular all the points on this line as cone? You can call it as a cone. Hmm. The set is basically this. I'm saying it is greater than or equal to 5. So this entire thing, whatever line. A cone can diverge, right? It's not about I can have a cone like this. It will keep on going in this direction. It can keep on going in this direction. All the points in this set, whatever, it can go infinitely in those directions, and still I can call it a cone. The problem here is it does not have origin in it. So if you take a point here, let's say I take a point here, then this will be the vector for that point. And then when I scale it, let's say this point is some 3 comma 1 or something like that. Now if I scale it to by say 1, scale it by 1.5 or something, such that it will come here. So like scale it by half, so 1.5 comma 0.5. When I scale it, it now it came outside the domain, outside this particular whatever this constraint says. So this is my set, but now when I scale it, it came outside the set, so it is not a cone. It is definitely a half space because it's with our definition. So this is basically A transpose X is less than, instead of less than or equal to, if you multiply with minus everywhere, then it will be a less than or equal to constraint. So this is a half space. So you can write this as minus 2x1 minus 3x2 is less than or equal to minus 5. If you write it in the form as A, this is A transpose X is less than or equal to B. So it is a half space. I cannot call it a hyperplane because for hyperplane I need an equality constraint. Okay. Okay. Now what about this? X2 equal to mod x1. I think if I draw this, it will be very clear. x2 equal to mod xn will be something like this. But then since it is an equality constraint, it only has points on these lines. No, nothing else. So can I call it a cone? I can call it a cone because it has origin, and if I take any point and scale it, it will still lie on the same line. Okay. Can I call it a convex set? Okay. If I take a point here and take a point here, and then take a linear combination, then it will be somewhere on this line, right? And that line is not in the set. The set is basically the points on this line, x2 equal to mod x1. Yeah, so it is not convex. Yeah, it's only cone. Okay, this is all again, this we have just seen. So you have two half spaces. When I take an intersection of them and create a new half space, will it be convex? Or let me put it in this way. Is half space always a convex set? Yeah, half space is always convex. So intersection of two convex is always convex. So that will be true. Yeah, now comes the concept of convex hull. So you have a certain collection of points as 1, 0, 2, 0, 0, 1, 2, 1. With these points, now I'm asking if is 3, 2 in the convex hull of S. So just like F and hull, convex hull is also the same thing. It's the smallest thing that you can wrap around that one. So if I just plot these points, you see I'm kind of solving all the problems by drawing on a plot. This is very easy when you have a 2D or a 3D problem. But you will have so many variables to control. For example, just you take the case of your CFD problem, your variables are U, V, W, and then temperature. And then you will have so many other variables also. Say entropy if you want to find, enthalpy you want to find, like so many other variables will be there. Then it will be a very high dimension problem. You cannot always plot and do. How to, yeah, in those cases, what we have to do is we have something else. We'll discuss once we solve maybe in like 6th week or 7th week. But for now, let's say we have these points 1, 0. This is basically a square. So I'm saying only these points are there in my set. This is just a collection of points. These lines, okay, maybe I shouldn't draw them. Or, lines are there, but lines are not part of the set. My set is basically these 4 points. Now I'm giving a new point 3, comma 2. 3, comma 2 will be something here. So it is not lying in the convex hull, right? So if I draw the convex hull, so these lines, whatever with these lines I draw, that will be the convex hull, because that is the minimum I can get over here with. Right, you cannot keep any curve, because the moment you keep a curve, you'll have points moving outside of it. So curve is not a convex set. So the minimum I can do is draw a line, and this is the line that I can draw. So this is a surface that will eventually form. The convex hull is basically this line that I have drawn here with these points. So with these points, 3, comma 2 is lying outside the hull. Yes. Okay, so I have two matrices A and B here, and I'm defining AX less than or equal to B. So this is definitely a half space. So like when I write it is in this form, A transpose X less than or equal to B, then it is a half space. So I'm calling it as a polytope. So what is a polytope? No, polytope is basically is a bounded polyhedron, right? And polyhedron is basically intersection of your half spaces. So here, is this a polytope with this A and B? So if you write this separately, then all I have is 1, 1. or I'll write it as x. The first one will be x plus y less than or equal to 1, and then I have x plus 4y less than or equal to 1. So this is one half space, this is second half space. And when I write this as ax less than or equal to b, both of these have to be side space. So this is the intersection of two half spaces. So that will be a polyhedron. All I want to check now is whether it is bounded or not. If I draw them, one will be like this, the other one will be something like this. So the intersection will be something covering this entire thing. It's like it will have something in second quadrant, it will have something in third quadrant. So, and this keeps on going in this direction. So this is not bounded. So it is not a polytope. Again, just to reemphasize, again, it is very easy when I draw all this and stuff, but you cannot always draw. So that is something you can ponder upon. So is the polytope always a convex set? Yeah, because it is intersection of polyhedron, it's intersection of half spaces, which are again convex. So intersection of convex is convex. I think these are the questions that I have for this. Yeah, these are the questions I have for this week. To summarize what we have discussed, we initially started basically with saying transformation. All we wanted to do is identify the equivalence between the problem. So if you solve one problem, you actually got the solution for other problem as well. So these are different cases we have seen. Scalar multiplication is where all the constraints and your objective function is multiplied with some positive scalar, and equality constraint is multiplied with a non-zero scalar. Then your problem will, your feasible region remains the same, so your objective will not change. One-to-one mapping is essentially when you have x equal to some phi of c. So essentially you're transforming from one coordinate to another coordinate by some transformation. As long as that transformation is a one-to-one transformation, we still have the same optimal value. A monotone transformation is where you have an non-decreasing or continuously increasing function. When you do such kind of transformation to your variables, your constraint are also accordingly satisfied. Then your solution will also remain the same. The next one is the slack variables. When you have an inequality constraint less than or equal to 0, you add a non-negative value to that inequality constraint to make it equal to 0. So your inequality gets converted into equality constraint, and then you can solve the problem. The next one is the linear equality constraints. In this, what we have done is we have written the essentially my hj of x equal to 0. These constraints we have converted into ax equal to b form, and then we kind of did some variable manipulation. So eventually you can reduce the number of dimension of your problem. Once the dimension of problem is reduced, all your equality will be removed, and then you'll have one objective function and a set of inequality constraints. Only those things are what you have to solve for, and your dimension is also reduced. That is with respect to linear equality constraints. And then once you have the scaling is again the same. It's the same as here. So if you do the scaling, nothing is going to change. And then we define the different concepts in convex analysis. Affine set is basically you take a linear combination of 2 points, and then whatever the resulting point, if it also lies in the same set, you call it an affine set. A relative interior is basically you take some arbitrary dimension, you take a ball of radius r, and then you take an intersection with the affine hull, and that intersection is what we are calling the relative interior. Convex set is again same as an affine set, but the only difference is in a convex set, your alpha value, the weighing factor, should always be between 0 and 1. A cone is a set in which you take a given point and then you scale the point. The resulting scaled point should also lie in the same set, then you call it a cone. A hyperplane is very regular to what you see in the 3D one, but then the only difference is you have n-dimensional points. So it's still A transpose x equal to B. Instead of 3D, it will be some higher dimensions. A half space is same as the hyperplane, but then you only consider only in the one direction than the other direction. So you take A transpose x less than or equal to B. So only half the points are included and the remaining half are negated. A polyhedron is basically intersection of all these half spaces, and a polytope is once you have a polyhedron which is bounded, then you call it a polytope. And these are the main things that we have discussed in this particular week. Yeah, I think there are no further questions. I think we can conclude the session for today. You're welcome. Okay, we meet next week in the same time. Thank you for joining.